Hi, we are Team Seascan, and our project is the Vacuum and Temperature Monitoring Sensor, or VTMS for short. Our technical directors are Richard Arthur and Peter Jones, and our consulting technical director is Mike Smith, a URI graduate. I am Chris Alexander, an electrical engineering student. With me is Michaela Belisle, also electrical engineering, and Mariah Messenger, computer engineering. Seascan is a small company located in Falmouth, Massachusetts that manufactures oceanographic instrumentation and equipment to be used primarily in scientific research development. They create a number of pressure-tolerant enclosures, which is our main focus for this project. The pressure housings are used to protect electronic equipment and battery packs when submerged in water. Once fabricated, Seascan will pull a vacuum on the housing and monitor it for 12 to 24 hours as a pretest to ensure it is functioning properly. The pressure housing is then sent to the customer. However, they will have no way of knowing if it is properly sealed after opening and closing the housing. This project is driven by the need to guarantee the enclosure is sealed every time it goes into the water once it is in the hands of the customer. The anticipated best outcome is a functional prototype that can monitor vacuum, temperature, and humidity levels and report the status to the user. A GUI application will be created to display sensor data, remaining battery life, and accept user inputs. The system needs to be able to send and receive data between the main circuit and GUI application via Bluetooth or Wi-Fi connection. A system user manual describing the hardware and software components will accompany the prototype, along with test results and a demonstration of the working system. Seascan's pressure-tolerant enclosures are essential for oceanographic research, and the ability to ensure the performance is even more crucial. As the company seeks to expand the market of the products, they will need to meet the demand for monitoring and collecting data from these enclosures. The first and most substantial step towards doing so will be developing the VTMS and a complementary application to it. This would ultimately improve the product's reliability, longevity, and increase its value. This is the block diagram of our proposed system. It shows the components to be included in the main circuit and how it will interact with the GUI application. We will discuss further on the different aspects shown in the diagram. Transitioning over to the hardware selection, we will be using a magnetic switch known as a reed switch in order to initiate turning on or waking up all the hardware. The switch selected is the MDSM 4R1218, as it is cheap and effective at doing its job. The picture shown here shows how the reed switch will be connected to its surrounding components on the custom PCB for this project. The 2-pin connector labeled J3 will be another switch or button to perform the same function as the reed switch, and the net labeled named D2 is the connection to the ESP32, our chosen microcontroller. The other electrical engineer, Michaela Belisle, will now continue discussing the hardware selected for the main circuit.
We went through a few options for the microcontroller and Bluetooth module, and in the end, we were able to find one board that included both and had all the features we need for this project. This was the ESP32 development board by Espressive, which included classic Bluetooth, BLE, and Wi-Fi connectivity, along with a number of peripherals. We decided on this board because of the wide variety of functions that would allow for more flexibility with the project. In selecting the hardware for sensing vacuum, temperature, and humidity levels, we had to take into account the pressure levels the hardware would need to read and withstand. The typical range of Seascan's pressure housings is -15 to -10 inches of mercury, with maximum housing vacuum of -25. This translates to about 15 to 20 inches of mercury in absolute pressure. We decided on the BME280 by Bosch, an environmental sensor that is able to monitor temperature, barometric pressure, and humidity. The barometric pressure sensing range is about 8.8 to 32 inches of mercury, which satisfies the project requirements. An initial prototype was assembled to evaluate the selected hardware before creating a custom PCB. This prototype included the ESP32, the BME280, the reed switch, a real-time clock breakout board, and a micro SD card breakout board. The ESP32 is flashed with Arduino code, which initializes the real-time clock with the current date and time, then collects sensor data every few seconds and stores it on a micro SD card and also transmits it to a BLE client device. The real-time clock, or RTC, was purchased as a second option to the ESP32 onboard RTC. This way, the RTC could be powered separately from the microcontroller and used to wake the main circuit from deep sleep. The microSD card is also a second option to the ESP32 onboard storage. By having this, the user is able to easily plug the microSD card into the computer to download the data. We needed to find a way to establish wireless communication between our main circuit and the user's computer. After investigating the Wi-Fi, classic Bluetooth, and BLE capabilities of the ESP32, we decided that BLE would be our best option. It is supported across a variety of operating systems, including mobile, which provides the opportunity for our system to be compatible with many types of devices. Power consumption was also an important factor to consider, and BLE is a low-power option that ultimately met the data transmission requirements of our project. There are two types of devices with BLE, the server and the client. The server device will advertise its existence, and the client device will scan for devices to connect to. Data can then be transmitted between the two devices. A generic attribute profile, or GAT, is used to define how the server and client send and receive data. Within the profile is one or more services that contain at least one characteristic. The characteristic has attributes including properties, value, and descriptor. The value will hold the actual data, and the properties provide information about how the value can be interacted with. For our project, we used the Arduino IDE to create a BLE server device with the ESP32. Shown here is the generic attribute profile of the server. There is one service with three characteristics for the temperature, pressure, and humidity. Within the characteristic, you can see the properties and the value being stored. Moving forward, we will be further developing this firmware to include the timestamp data along with the user inputs from the application. Mariah Messenger will now discuss further about the BLE connection to the application.
The remaining task to achieve our anticipated best outcome was to create an application with a graphical user interface that would allow the customer to interact with our PCB so they could gather and analyze data. The first step in building the application was realizing its behavior. To communicate with the ESP32, it accesses the PC's Bluetooth and advertises its existence through a Bluetooth low-energy script written in Python. After some fine-tuning, the application will also be able to successfully send and receive data packets. Once a data packet is received, the Bluetooth low-energy script will process the data based on its attributes, as Michaela described previously, and store it into a database. MySQL is a database management system that can be implemented in Python, which is what we will use to process data coming and going from the database. From here, the graphical user interface can display data upon request and also write parameters to the database to be sent back to the ESP32. Before beginning to design the graphical user interface, multiple Python toolkits were evaluated, and Tkinter was chosen based on its compatibility. After that, a skeleton was created to provide a foundation that can be built upon. Some basic functionalities were realized, such as the ability to connect to a device, bring up the File Explorer, and clear the contents of text box widgets. The graphical user interface will also allow the user to set device parameters and monitor sensor readings in real time. Specific ranges or periods to log data can be set, and the data can also be read or cleared from the device connected. Moving forward, managing data will likely be our most difficult task. The Bluetooth low-energy capabilities of the application must expand to establish communication with the ESP32. This code must be able to connect to a Bluetooth low-energy server, then interpret and process any incoming or outgoing data appropriately. The graphical user interface will need to monitor the database and display any data when necessary. Once the application is complete, a distributable file will be the final step in creating it. The firmware will need to be modified to interpret and process data in an inverse manner and include all the features of the final system. Low power mode functions will be added with an external wake-up for the read switch and a timer wake-up for the user-defined sensor reading frequency. The battery life will also be monitored and recorded and be sent to the graphical user interface to display. A series of LEDs will be added to the main circuit to indicate whether the vacuum, humidity, and temperature levels are within the user-defined range. Using a program called Circuit Maker, the components from the evaluated prototype will be placed and wired on a schematic. Then, a custom PCB will be designed by placing and routing the components using the PCB design tool on Circuit Maker. An additional external circuit board with LEDs will also be fabricated for use with non-transparent pressure housings. Lastly, we will design a user manual to document the functionality of our system. This manual will walk the user through how to operate the hardware and the graphical user interface. There will also be documentation of the firmware and software written for the system. In conclusion, we would like to extend a big thank you to the following people: our technical directors, Richard Arthur and Peter Jones, our consulting technical director, Mike Smith, and of course, Dr. Sunak, our Capstone program director.